are we ready?
Oh, I got your microphone.
No. Is it on as well?
Doesn't look like it. That's it. There we go. Can you hear me?
Okay.
All right.
So we've got one big talk and one little talk. Yours is a big talk.
Is it? Okay.
And then we'll break into all the workshops. So if we can get on with that now. This is Ara, who's Arco Online. He has come across from the US to tell us about how they do things there. But we all know that he's slightly in awe of us, so it's fine. And actually, I mean, I will, let you carry on, maybe.
Okay, cool.
Great.
All right, so this actually isn't heavy payloads. I set out to try to replicate the conditions of near space. This is all totally for fun. And I would not recommend, this is like a disclaimer, I would not recommend making, you don't need to test using vacuum chambers and whatnot that I'm about to show, but anyway, so. All right, so the first thing I would want to cover if you're going to talk about trying to make your payloads more reliable is failure, right? Why do things fail? You're much more likely to fail because of software or radio or power configuration, far more likely than the environment is to kill your electronics. So just so you know. The roadmap I took was kind of like this. Understand the environment, so that's what I'm going to go over is kind of what the environment is. Understand the hardware you're going to be using, determine tests, build it, test it, and then analyze what you get out of it and redesign after that. These are based on the international standard atmosphere. You have air temperature, which varies anywhere from -60°C to about 40°C. By the way, a lot of this may be a little obvious to most of you, but this would be helpful for new people. Pressure, 1 atm to about 1% of that at 30,000 meters. Winds actually can go above 100 miles an hour, especially at the higher altitudes, up to 200 miles an hour. Forces, you're more likely to experience the largest forces when you hit the ground. Humidity, if you're launching from the desert, where I usually launch from, it's near zero, and if you're here, it's, for some reason, there's water in the sky. I don't get that. Solar irradiance or solar heat is 180 watts per square meter to about 340 watts per square meter. And radiation, you can completely forget about. I did some math, and it turns out you need to fly your HAB for 10 years for radiation to actually knock out one of your chips. Not going to happen. Thank you, magnetic field. The environment, if you wanted to kind of lay it out, looks like this. You have radiation and convection. And for radiation, you have solar flux coming in from the sun. You have the heat of the earth, so you have IR ground. You have IR from the sky. And then you have albedo, which is the sunlight bouncing off clouds and off the ground. And obviously you have air convection. Except after 18,000 meters, it turns out on a few models I looked at, after 18,000 meters, convection drops off. Your air temperature is actually not going to affect the overall temperature of your HAB as much as all these radiation factors are. And here are two graphs that kind of put things into perspective, I guess. This will need a little updating. Turns out you need to add Babbage up there. I thought it was. So you can see pressure dropping off, obviously, around 18,000 meters. This is kind of the line you want to, or 18,000, yeah, wait, 18,000 meters. I'm trying to get my SI units right here. And the temperature actually gets coldest around here. And it starts to heat up again. After, it doesn't even matter, but the ozone layer starts absorbing a lot of that UV heat and from the sun, so the air temperature actually increases and then drops off once there's practically nowhere left. The right side, thankfully I got permission to use this graph. It's a graph that shows the heat flux from the ground, the sky, and as you can see, sky drops off as your altitude increases. But the ground provides a wonderful, nice, constant heat source almost. That's what's really keeping your HABs alive at night, preventing it from going to like -200 degrees Celsius and dying. And you can see albedo really doesn't make that much, doesn't really play that big of a factor into it. So the next thing when you're designing hardware is you obviously want to look at your data sheets. You want to know what the operating temperatures are. You want to know how much, if they are going to generate heat. And from that, you can get an idea of if your HAB is more likely to overheat at 30,000 meters or if it's likely to freeze to death. And usually it's things like power regulators, powerful processors, things that generate heat, and low power parts that are drawing milliamps are more likely to get very cold. So I came up with 3 tests that would answer questions. The first 2 are really easy and can be done for $10. The third one actually requires a little bit more money. The first one being, can your HAB survive the temperatures? Most parts are rated for negative 40 C, and you go up to 80 C. How well does your insulation work? And then will your HAB overheat? So again, power regulators or any new technology you're not sure of. It's just a mystery box. You don't know how it will interact at high altitudes. This chamber might help answer those questions. I try to do thermal modeling, but you really have to have a good understanding of physics to get something accurate. And even then, it's not 100%. You really do need to test it to find out. Right, so just test it. The room temperature dry ice test is the most recommended test that I would at least say you should do for anything you fly. Is wrap it with cloth, put some dry ice against it, and get it, and make sure you have a temperature probe to look at if it gets to the, you don't want to go below the operating temperatures and potentially harm your hardware. And then you could use a hair dryer and heat it up and look at the performance, if things drift around, what's going on when you do that. And if the question is, will it operate differently at vacuum, then you're going to need a vacuum chamber. I set out to do this design here. Air temperature you can replicate with dry ice, and if you really want to heat it up, use a hair dryer. For pressure, I used a refrigerator. Actually, I didn't use a refrigerator pump. I ended up switching from a refrigerator pump to a better pump I found on Amazon. For heat, I just use a light bulb, and if you move the distance back and forth, you get a different heat flux through applying to it. For winds, turn on a fan. If things start blowing off your HAB, that's bad. Forces, I love Ed's method. I'm going to call it the Ed method. I don't know what it's actually called, but throw it down some stairs, and if it dies, then you've got some problems. And humidity, I guess a spray bottle inside, and that's actually pretty difficult to replicate, but in the end, at the end of this, I'm going to have a solution for humidity, or you don't ever have to worry about it again. So you take your HAB, you put it in some insulation. The design I had was, I tried to go anything off the shelf you could just buy at a hardware store. That was kind of the challenge. I used a Schedule 40, I don't know if that's international standard, at least in the US, there's Schedule 40 PVC. And I used a PVC tee, some silicone rubber, half-inch, except 12.7 millimeter polycarbonate glass, woo, metric, and a vacuum pump. By the way, for all these parts, I have a list on my website, which is at the end. So if you're curious where to get all the materials and whatnot, that's all at the end. I have a link for that. The original design had a Peltier cooler, a heat sink, and a heat transfer rod, but that ended up not working very well. And there's the light bulb for producing heat. So here's kind of the schematic of it. I tried to get one side of the HAB very cold and the other side of it warm, and see what would work best, and kind of understand if, because as far as the electronics are concerned, because this is conductively coupled, right? It's not radiatively coupled like it would be for true deep space and the ground and whatnot. But as far as the electronics are concerned, that would be okay because it's under that vacuum and it's cold. So anyway, the heat transfer rod didn't work very well. There was like a 40-degree difference between the cooling and the rod itself. So I ended up using fishing line and taped dry ice to the HAB and put cloth between it so I could vary the temperature by just adding more layers of cloth. And the only thing is you have to run this continuously because the dry ice is sublimating. So the pump, by the way, if you do choose to use any other pump, you got to make sure it can operate without air. It's an actual true vacuum pump. So a lot of those rely on, normal pumps usually rely on the liquid that's flowing through it to cool it down. So here's some pictures. I have tons more pictures. I've took 200 photos. They're all on my Flickr. You can take a look at it in every possible angle. So you can see the HAB on that end. I taped one temperature sensor on the front, one on the back where the dry ice is, and then one inside. Plugged it all together, I even had the heat lamp here and a Yagi actually holding it up. And if you really wanted to go through the efforts, you could do EMC testing while you're doing this. This talk, by the way, was an hour long before, and I had to cut out a bunch of slides. And I really emphasized on EMC. So if you really want to learn about EMC, my extended edition of this slide on my website is on there. You can learn all you want about EMC. So yeah, measurements. I had a pressure sensor on there. I tried to make it easy. I used an Arduino. And the plates, I laser cut, but if you're using plexiglass, you can just drill through it, unlike acrylic, which will shatter like crazy. And then I ran K-nar wire through that, and then I just put epoxy on that, and it holds pressure for a couple hours, so it's pretty good. I was surprised. I was looking at like vacuum, safe like connectors, and they're hundreds of dollars. I'm like, nah, it's not gonna work. Too expensive. So here's the results. I had to cut out a bunch more results, but this is like the good hey, it kind of works test. This is I got the pressure down to about 2 kPa. 1 kPa is 30,000 meters. So this is in a vacuum, and the deep space side got down to about -40. The hot side facing the sun got to a nice cozy 30. And you can see the internal temperature slowly dropping down. That eventually got down to about 5 degrees Celsius. So you could definitely see thermal extremes and kind of replicate those conditions. However, if you wanted to improve this design, the real way to do it, the way NASA does it, and I guess anybody else is doing real environmental chambers, would be a thermal shroud where you run liquid nitrogen, isopropyl, glycol, whatever you want to use, to cool the walls and have the insides coated with something that has really high thermal absorptivity, so you have good radiative coupling between your HAB and deep space. And probably throw that on a control system. This heat sink is very crazy. That's a Peltier cooler, by the way. It's for like street racing cars or something like that, where they wanted to pre-cool the intakes or whatever. That thing is way overkill. I was planning on using that. I'm like, it's out of budget for most people. And then a Lazy Susan to kind of move the HAB around, because your HAB is not going to be facing the sun the whole time and deep space on one side. You're not going to get those thermal extremes. It's spinning around and going crazy. So how do you solve these problems? If you know you're either running a hot or cold HAB, how do you solve these problems? The basics would be, if it's a serious problem, a lot of the time you can kind of throw some conformal coating and press it against your insulation and get some decent conductive coupling to your insulation. That might help you dissipate the heat. But if it's a real problem, radiators, something with metallic that'll conduct that heat over to a painted surface that has high emissivity, and you could throw that radiation out into either deep space or sometimes even the ground. Because your HAB is headed up and the top is always facing the sun, you don't want to put your radiator facing the sun. The ground is going to be much cooler at really high altitudes. Software you could obviously use to turn things off. That's another solution if that's a option. And then aluminum foil or something that reflects away any radiation. So you want to get rid of as much heat coming in from the sun as possible, since you're running hot. If you're cold, it's really simple. Just insulate it really well. Extruded polystyrene. I found Foamular, which seems to be one of, I don't know what the equivalent here is in the UK, but they sell those at Home Depot where I am. It's a great material. Paint it black. Try to make it absorb as much heat as possible. And if you want to use a heater, you can, but that's going to waste a lot of power, and you probably want to put that on some control system that will go, hey, I'm getting cold, let's warm myself up. Otherwise, you're going to waste all this battery power. There's different thermal insulations you could use. Spacecrafts use MLI, which is this fantastic material, which is just Mylar, Kapton, and polyester mesh, where any solar radiation will be reflected off, and the mesh creates this really small conductive, thermally low conductive. I can't speak. It minimizes the conduction. That's what it does. And this stuff has, like, in terms of R value, it's ridiculous. Like, you could have thermal extremes of 200 on one side and -100 on the other. Or you can stick with whatever foams you want. There's obviously a link to the UKHAS materials website. That is a great source. Conformal coating, I would use it and I would recommend using it if you can. It's essentially this material you put on your PCB and it protects all the electronics. One of the nice advantages to that is if you have parts that don't really have heat sinks or they're generating enough heat but where they could possibly overheat, by adding this conformal coating, you actually lump it together thermally. So it kind of acts as a heat sink. And it prevents corrosion, humidity. That's the solution to the humidity problem. If you conformal coat it, humidity is not really going to bother you. I highly doubt you're going to see whiskering. Whiskering does occur. It's a really weird phenomenon that no one knows why it forms, but for some reason it doesn't. It's killed spacecraft before. So conformal coating will kind of dampen the effects of whiskering, but it's not really the important part. And accidental shorting, especially if you have wires around and stuff, you don't want things touching your board and killing it. I have a link here if you want to learn how to properly apply the conformal coating. There's 3 kinds: acrylic, silicone, and urethane. I've used silicone a lot, but urethane is also great. That's used a lot in spacecrafts as well. So that's another option. And I think that's it. Hope I didn't run through this too quickly. So if you go to the site, it has my extended edition with everything that you ever want to know. If you want to know more, just hit me up on IRC. I don't know. So, questions?
With the conformal coating, I guess it's a one-way trip, though, isn't it?
It is. That's the problem. So, if you should conformal coat once you've debugged everything. And I had that happen before. I discovered a bug after conformal coating it, and I conformal coated. You can. There's techniques where you can put tape over connectors and prevent conformal coating over important stuff. So yeah, you can tag it, but if there's a major problem, like you need to run Kano wire from this thing to that thing because you forgot to wire it, it's game over. Like trying to get that stuff off is a big pain. Yeah.